Hello. Hello. Can you hear it? All okay with your Thursday test or exam, whatever that was? Who still stumbled a little bit here and there? Put your hands up. Any particular reason? Any reason for? That's fine. Anything else? Looked at the table. Do a little practice, yeah? Practice on the looking at the table. That time does something there when you come and sit there. Told you many times already. Don't come there and try to wing it, yeah? It looks easy here in the class. And because I came to your tutorial class, I see that you take your own sweet time. You should put a clock on yourself. And the problem is given in the tutorial, you set up a timer for yourself, pretend like it's a question in some test or exam, and then sit independently and work on it. And if you're still confused, you're not getting the numbers, put your hands up, call the tutor and ask the question, yeah? That actually is meant for you so that you don't have to prepare separately for any exam in this course. Do you understand? That is what the tutorial is meant for. It's already you're done, you're ready for the exam. If you're still preparing one day before the exam now when the midterm comes, then that means something's not gone according to what it should go to. Practice. Anything else? Anything that tripped you, surprised you? I've not looked at the question paper. I think it's something that's easily doable. That's what I would think. So were there any conceptual questions? No. Okay. I think there's one more exam coming up, right? Before the midterm? I might have a small hand in that, maybe. So let me see if I can check some concepts. Yes? I will. So go back, let's finish up heat capacity, and then today and tomorrow, next class, we'll do some problems with chapter 5. Correct me if I'm wrong. It's midterm is up to chapter 5, huh? Sure? Okay. Then we'll spend one more Tuesday on chapter 5 and then I will move to chapter 6. It's fine. Okay, again, rehash. Write down your, we cannot measure absolute values. We can measure only change in value. So you have constant pressure, heat capacity, and so you very nicely told what are the factors of heat capacity that affect heat capacity last class. And I think one of your friends told the most important thing. The first point, heat capacity is primarily dependent on louder temperature. So just don't forget that part, because enthalpy will change your temperature, internal energy will change. Actually, sequence is wrong. Internal energy will change with temperature. Then you might possibly do work. Enthalpy will change with temperature. So both the heat capacities will change with temperature, both CV and CP. Now let's do a little bit of ideal gas CP CV. So will ideal gas work at every temperature and pressure for all the materials? Will it be an ideal gas situation? So 2 marks questions like this. What condition would specify ideal gas scenario for most of the materials? It should be a one phrase answer. That's all. Lowest pressure. Lowest pressure, minimal interaction, ideal gas. Ideal gas is a non-interacting system. You consider them as balls, hard spheres. They don't impinge on each other. There is no any kind of attraction or interaction. Just maybe elastic collision. That's all. Hard sphere. Non-interacting system. So lowest pressure. That should be a very simple answer. Sort of like a ideal zero pressure. So what these guys do in the book and in your numericals is, whenever it is for ideal gas, they will put one more subscript here for the heat capacity. Just be careful, yeah? So they will put, so that 0 is like, or O is like, or it's a 0, it's zero pressure. Got it? There's 0 here. Write it. Better if you write it. Subscript 0 is all ideal gas. Zero pressure heat capacity. Zero pressure constant. I mean, it doesn't even make sense. Zero pressure constant pressure heat capacity. Sounds funny. Zero pressure constant volume heat capacity. Just a notation. If it is not there and they simply keep giving CP, CV in the numericals, you should one time confirm and ask, should I consider this to be ideal gas or non-ideal gas? Those things you are welcome to ask. Yes? So if mass is given, what will you do? Now if the mass is also given, you know the units of, one more time, units of heat capacity? Quickly. Don't trip over these things. It's the entropy units. Joule per, and it's an intensive property or extensive property? Internal energy is an intensive property or extensive property? Extensive. Enthalpy is intensive or extensive? Heat capacity would be intensive or extensive? Extensive. So what should you need to do? What else? Grams. Joule per gram. Specific heat capacity, yeah? This is intensive, correct? This is intensive. You have already divided by mass. Can I just divide by mass? Can I even have molar? Can I have molar per mole? How do I convert this to per mole? Should I multiply by molecular weight or should I divide by molecular weight? Pretty simple. Huh? Sure. Gram per mole, multiply by molecular weight. Well, how did you get R to become R bar? Divided by? Why? No, not divided by mass. Divided by molecular weight. So what's the unit for R at that time? 8.314 what? No, tell me the full units. Come on. What's the entire unit for 8.314? 12th standard question. Huh? Joule per Kelvin per mole. Sure? Not gram? Joule per Kelvin per mole. Okay, how do I convert that to mass? How do I convert that to mass? Joule per gram. How do I convert Joule per Kelvin per mole to Joule per Kelvin gram in your 8.314? Do I multiply by molecular weight or do I divide by molecular? You divide, got it? Otherwise don't trip on this. So somebody asked me after the class, last class, so if R bar, what should I do if that molecular weight of that refrigerant is not given? So you should ask for it and get the number, okay? So molecular weight is, if you want to do R bar, then you have to ask for molecular weight. So here it's a reverse. Is it right? I'm converting joule per gram, degree Kelvin to joule per gram mole. How do I do it? Multiply by molecular weight or divide by molecular weight? No man, look at it. Should I multiply by molecular weight or divide by molecular weight? I need to convert this to joule. What should I do? Multiply, got it? So ask for the molecular weight, yeah? If you need to use these units, ask for molecular weight. If you just want to leave it as gram, it's fine. And this is a specific heat. So if a mass is given and you are asked to find the change in entropy by using some heat capacity, what will you do? But this is per gram. What should you ask for? I'll give you the mass. I'll say 1 kg. I'll say 1 kg. I want the enthalpy only in joules. I don't want it in joules per gram because I'm giving you the mass. I will say for 1 kg of this air, what is the enthalpy change if I change temperature? Where should I put the mass? Here, here, here. So then your units is just joule. Specific or absolute. So then what will I write for D, U? I'll put a 0, I'm talking about ideal gases. So in some problems you will have consider the mass of the cement block, consider the mass of the stone block. So it's an extensive property, clear? Yeah. So now fun stuff. You said it's a function of temperature. Anybody knows how Cp varies with temperature? We already did this last class. You know the trend. Does it decrease with temperature or increase with temperature? Huh? Increase. Obviously, the dispersion will increase, you will have more mobility if you have higher temperature. Very good. And that also means with a physical state, if I have solid, liquid, gas, is it a ascending trend or a descending trend? It's ascending trend. The heat capacity will increase as you go from solid to liquid to gas. Yes. And the heat capacity will increase with temperature. So anybody knows the history of who came up with calculations to show how heat capacity changes with temperature? Some history of heat capacity. Anybody knows? Or did they measure it? They took air, then they measured it, then they took carbon dioxide, then they measured it, then they took methane, they measured it, then they took nitrogen, they measured it. Or do you know of two maybe the most famous models of heat capacity with respect to temperature? Do you know? No? Who considered all the vibrating atoms like oscillators? Would you know that? Who considered all the atoms vibrating like simple springs, oscillating springs, oscillators? Which particular scientist, little general knowledge, which particular scientist considered vibration of atoms like oscillators, like springs? Don't know? Okay, a little bit read up on the history, it's interesting. Einstein, he considered the vibration as oscillators. And what he did was wonderfully, he made the oscillators, the number of oscillators that vibrate as a function of temperature. So at low temperatures, all the oscillators will not vibrate. As you go along and increase the temperature, what happens? More and more oscillators vibrate or less oscillators vibrate? more and more. So then what happened to heat capacity because of the oscillation? They nicely dispersed the energy. The heat capacity began to increase with temperature. But this is sort of like it's a very good model. It actually comes very close to experimental data, but it misses the experimental data a little bit here and there. So another scientist decided, I'll just modify this Einstein model. What do you think he might have done? Einstein said, let's consider all the vibration of atoms to be like oscillators. And as a function of temperature, some amount of oscillators, then more amount, then more amount, then more amount, then at a higher temperature, everybody is activated. And he said it's pretty good. It will match with your experiment. It does. Little bit at low temperatures, it deviates. That's where the funny business happens. At low temperatures, it deviates. Einstein model, everything appears like it's dead. It comes down very fast. But in real life, it doesn't come down that fast. There is still life there. So another scientist modified this. What do you think he might have done? No, they did not go with any collisions, bond formation, friction. They didn't, it's just the beginning days of understanding heat capacity and dynamics of atoms and molecules. These are the beginning days. What? So one more thing. Einstein said all oscillators are sort of similar. They all vibrate at one frequency, single frequency. So when somebody does it, what do you do? Because you think you know real life a little bit better than Einstein. So you think of a real system and what do you do? No, resonance and all is. So you will think there must be a distribution of frequencies. So Debye came and put up one distribution of frequencies. He said most of the real materials will be oscillators when they're vibrating, but they need not vibrate at same frequency. So wonderfully in that integral he put distribution of frequencies. So what happened was at low temperatures you still had some frequencies alive. They were still alive. So the heat capacity was much higher than, his heat capacity was much higher than Debye's was much higher than Einstein's. So like real world, it was still there. There was still mobility there. But in Einstein's it just froze up. So how do the trends look? How do the trends of these plots look? I think this you might have seen in some book. CP, so people usually divide by R to make it a dimensionless number. Yeah? Dimensionless number. So they usually go up like. So different materials go up to different values at different temperatures. So I told you something, right? It will get a qualitative information when you look at these plots. But now I'll come back to something that I said last class, that when you have heavier atoms, then they will cluster, then their mobility will decrease, and the heat capacity will come down. So I have a surprise for you. So if you have more vibrational modes, will you have higher heat capacity? First question. Yes. So for you to have higher vibrational modes, should that molecule be a simple molecule or a little bit complicated molecule? Excellent. So with that in mind, this is carbon dioxide. This is water. And these are like oxygen, nitrogen. So their heat capacities are lower because the number of vibrational modes of simple molecules are lesser than complicated molecules. But now, all of you know that the greenhouse, a little bit you know about greenhouse gas, right? The one that holds heat and throws back heat and keeps your ground temperature a little bit hot. So what did I say in regards to heat capacity? If you had high heat capacity, would that material keep your system hot or keep it cool? Keep it cool. It has high heat capacity. It can take more. Temperature will not rise. So which one is hot here, high here? Carbon dioxide. But the same carbon dioxide is also a bad boy, yeah? So how will you answer this question? Its heat capacity is high, it should give you comfortable temperatures, but then it also messes up, which is what the biggest pollutant byproduct is, carbon dioxide. So what's going on? It has high heat capacity, but it's a greenhouse gas, a very major greenhouse gas. So what did I forget last class? Other than heat capacity, what else should you consider to check on the ambient conditions? I said heat capacity will tell you what you could have in the atmosphere because you know the temperature, correct? But also something else. I just said something else. The greenhouse effect. You should also consider what of these gases? Their ability to absorb a certain radiation from the sunlight and hold it and emit it back to Earth, back and forth, back and forth, back and forth, and you will have heat trapped in your atmosphere. That part also you should consider. Is that part heat capacity? Absorption and emission? No, that is not heat capacity. Got it? Heat capacity involves no work. Very negligible work. Very, very negligible work. You should not consider major work at all. Absorption and emission is work. Why is it work? It's more ordered and more oriented. You will absorb and you will have a vector and your momentum will increase and you will bounce really faster, and then when you're tired you will give back the radiation. Or you will conduct it within your system. Yes? So this is what I think we discussed when we were talking about conduction and heat capacity. Thermal conductivity involves work or no? Thermal conductivity is, it's organized work. The heat has to go in one direction and it should transfer the heat. It should do work. Heat capacity does not involve, in a very predominantly, it does not involve work. So even if you say CP, in the CP, the work contribution is very small. Got it? You're saying CP and you're writing H, and you're writing H as U plus PV. The PV is very, very negligible for heat capacity. That actually gets used up, that work gets used up for like a process like conduction or like absorption or like emission. It's not dispersion. That's what you said, right? It's not dispersion of the energy. It does not distribute the energy. That does not involve work. It just happens. It's spontaneous. It finds different modes. So one small thing we forgot. So carbon dioxide heat capacity is high, but it's also maybe the biggest culprit as the greenhouse gas, because we have to consider absorption and emission. So one small question before I move on. Water vapor is also considered as a greenhouse. And water vapor absorbs more than carbon dioxide actually. It has more capacity to absorb the sunlight because it has more modes that will absorb and do work. So water vapor does more work than carbon dioxide. But usually you accuse carbon dioxide more than water vapor. Any reason? Everybody blames carbon dioxide mostly, and then they blame water vapor. Any reason? Here the CP conversation slowly takes a back seat because we are talking about absorption and emission. That's why I put up the CP before. So carbon dioxide CP is much higher. Yeah, water CP is a little bit lower. But still you blame carbon dioxide, correct? Even if you take CP here, the CP of carbon dioxide is much higher than CP of water. So who should you blame? the work is less than carbon dioxide. No, carbon dioxide also does work, water also does. Water also does a lot of work. It absorbs more. No, comparatively also it has more absorption in the sunlight IR spectra, in the IR region than carbon dioxide. Denser, also you can, yeah, a little bit elaborate on that. Denser, which one will dissipate faster? So even though water vapor holds, it sort of dissipates faster than carbon dioxide. Carbon dioxide's lifetime is, I forgot, many, many years. Before carbon dioxide leaves your atmosphere, I think there is some X number of years. So it stays here for a long time. Water vapor dissipates much faster. So little bit, that whole cluster dissipating is also, that's what he means by dense. So that also should dissipate faster. Otherwise the hot spots will not move out. You get hot spots only when you have something aggregating in different places. Then you get hot spots. They should also disperse. So since all this harping led to one take-home message, that Cp is a function of temperature, yes? Correct. So now in your numericals, what will you do? Because who is to give you this equation for different materials? Somebody first has to go find these plots, then they have to fit it with some equation, and then they have to, otherwise, what will you do? Tell me, what will you do? For methane, let's say I don't know the plot, how Cp changes with temperature, so I don't give you the Cp as a function of temperature, but I will tell you find the enthalpy change between T1 and T2. So you will put H2 minus H1 equals mCp T2 minus T1. But I have not given you, so is that a good approximation to say Cp is constant between the two temperature ranges? Is it a good approximation? It's not a good approximation, but what will you do if I don't give you anything? So let me put that question back here. H2 minus H1 so you know T1, you know T2, you know H1. You're required to find H2. Obviously, you will ask me for heat capacity. I'll say, yeah, just take some value in a table. For T1, you take the value. What you will do? But then you will question and say, for T2, Cp should have changed, right? Then how do I do this? Will you compromise and say, it's fine, you have given me T1 value, I will just use the T1 value, and will you? But what will you do if I don't give you Cp? How Cp changes with temperature if I don't give you this? To make it fun, I can give you a plot and ask you to fit it there, but how you will fit it in the exam? You don't have a software there. What will you do? Come on. They turned off the timer there. What will you do? So you have three options. One is compromise, just assume Cp does not change with temperature, dump all the values here and find H2. You cannot do anything else, yes? Or I can give you an equation where Cp changes with temperature. Then what will you do? Then you will separate this as Cp_T2, Cp_T1. Then for each temperature you will plug in that equation, get the correct value of Cp, multiply it by T2 and multiply it by T1. Got it? Where are those equations in your book? It's there in some table. Whoever has a book, open the table. A.6. A.6. For some materials, you have the function of Cp So you have the equation for Cp as a function of temperature, A.6. Would that be a better improvement than just considering Cp to be constant? Yes? Okay. Would it be the perfect improvement? What would be the perfect improvement? Because what is this? H2. Correct? So you're trying to simplify this integral. What did you do to simplify this integral? You made this constant. Or what did you do? You asked for a function of temperature and then you use this integral. What would be the third way? What would be the third way? And that's the best way. That is also there in your book. What would be the third way? One is to make this constant. One is to ask for a equation. That still is that equation comes from just modeling. It's not exactly from the entire integral, but that is an improvement. Definitely an improvement from using a constant Cp. What would be the third way? No, but you are trying to find H. For a change in temperature, you are trying to find H. What would be the third way? Everybody get it? One is constant Cp, approximate. One is go to A.6, find the equation for Cp as a function of temperature. Slight improvement. What would be the best way? The so-called most accurate way? Because you have to have the entire integral. Then it's the correct way. Why use a model? Why say constant Cp? Why do all that? Can you somehow get this entire integral in terms of enthalpy? You can, but then what would I need? What would I need? What would I need? This entire integral I can measure. Literally, experimentally, I can measure and say that I've considered this entire integral of Cp dt between temperature ranges of something and something, and give you a very accurate experimental value. For that, what do I need to do? I said from something. You cannot do T2 minus T1 for what you need H2 minus H1. Then I cannot do it. Because that is the whole question, right? That's the whole point. That's the question. How to find the difference between H2 and H1. But for that I have to do what? I'll give you a hint. Can I find a reference temperature where I know the standard value of enthalpy? Yes? And then can I come to another temperature? So what you do is go to the next page. So if you have this issue here, how do you break this up? You take one reference to T2, get the experimental value, then minus reference, same reference, T1, and get the experimental value. Can I do this? And then I got H2 T2 minus H1 T1. So this is not coming from any equation, this is not coming from any equation. This whole thing is coming from experimental data. This whole thing is coming from experimental. Can I do that? Yes? Guys, yes or no? So where are those values where people have gone from a reference temperature and actually have measured experimentally the integral? It's there in A.7 and A.8. A.7 is for air, A.8 is for various other materials, carbon dioxide, ammonia, methane. This would be the most accurate. If you go to A.7 and A.8, you have the correct integral. So you're not assuming constant heat capacity, you're not assuming any equation as a function of temperature, you're literally getting experimental data out. From reference to T2, reference to T1. Subtract both, you'll get T2 minus T1. Yes? So if you want to be very accurate, go to, but you don't have that values for all the materials. So calm down. So if somebody gives you granite, paper, so then you have to assume constant heat capacity and compromise. Yes? Or you want to be more accurate, you ask the person there that, can I get a function of Cp as a function of temperature for that material? Worth it. If they have it, they will give you. So this is just so that you understand what could be a crude calculation to a so-called accurate calculation from using experimental data. That's it. I think we've slowly come to the end of chapter 5. So do we consider any time dependence here? Like, is the enthalpy changing with time? Is the temperature changing with time? Is the heat flow changing with time? Sorry, I said heat flow. Is the heat changing with time? No. Is the work changing with time? No. So you wrote a global equation, right? You wrote the microscopic energy, macroscopic potential, macroscopic kinetic is equal to whatever the heat that you receive minus whatever work you have done. You have not considered time there. But can I put a dt and consider time? You can convert that entire static equation to a dynamic equation. So somebody in a numerical might consider that this is changing with respect to time at a rate of. So don't suddenly think at a rate of, no, this is some other chapter here. No, it's not some other chapter. You just have to convert the static equation to dynamic equation. Everything changes with respect to time. So can you write that equation? I would like to see how you write that equation. Go back to your global equation. Go back for you. And then I will do problems Tuesday. So I have a lot of energy if I have heat. I lose energy if I do positive work, correct? So how do you convert this to time dependence equation? Write it one time. Everything is dt. So what's the notation usually in math when we don't want to show dt? What should I do to Q? Put a dot. So don't assume everything has to be independent of time. You may get a time dependent problem. Nothing, you have just converted, you don't need to look at it. Just take your static equation and dt it. It changes with respect to time. Yes? That's all. Your book is pretty good in certain things. I didn't realize. So, you know, all this, how to look at a problem, they've summarized and given you somewhere how to approach a problem. So can you please read, before I come for the next class, 5.4, just section 5.4, how to approach a problem. It's very nicely written. Section 5.4. Yeah, shoot off. Any questions? So what is the progress from 4th chapter to 5th chapter here? There you did independent heat and independent work calculations. Mostly you did lot of work in chapter 4. What happens to chapter 5? You have to start considering change in U and change in H. And then the heat capacity also comes in. Yes? So you have slowly moved from specific volume, and then from state 1 to state 2 you have learned how to see the specific volumes. Then you have learned to see whether it's constant volume, constant pressure, or whether temperature is changing or the pressure is also changing. Then you have slowly learned how to calculate the amount of work and learn to draw the phase diagrams of PV and TV diagrams. And then once you have done work, you learn to write the conservation of energy. So which means the balance that you have is the internal energy that's there in your material. So then it will come down to, after you have some heat and some work done, what is the balance that you have? That would be the internal energy or the enthalpy. So it's come down to that. That is where you are. So you have moved on from work to the balance of energy. And most of it you are doing in controlled mass. You are doing mostly controlled mass problems, but it can also be done for controlled volume, where the mass can change. That's why slowly you are introduced to the rate equation also, because the mass change could be with respect to rate, correct? Like you are blowing in the air balloon at a rate of, so the mass will change. That's where the control volume will come. But there the volume also changes in the balloon. But after a certain time the volume does not change in the balloon. The mass can change. Otherwise the balloon will break. Balloon can only expand so much, yes. After that you still go. So what happens to the balloon? It just becomes more rigid. The packing increases, that's all. Because you put in more mass. So right now you are all on control mass. I don't think there is any necessity to get confused. Anything else that trips you, that confuses you, shoot off. I will make notes of it and come back next class to clear it. Anything that still bothers you, feel free. You can shoot off, put your hands up. Anything in the phase diagram that's bothering you, what is left side, what is right side, what is at the center, what's at the top, why the line goes like that, why the line comes like this. Just don't hammer away at the numericals as soon as you see in the exam. That's all I'm afraid of. You can spend nicely 5 minutes, just calm down and write down the whole question in the corner at the side. You can write the whole, what the processes are, and then you can write the plot, and then you can do the numericals. Not aggressively go at the tables and say, let me go find the numbers. So I think you got some volume changes, did you not, in the exam? And these are all iso volume changes, am I right? Like isothermal, correct? So how does isothermal happen? If the phase is transitioning. And for that you also have to have one device continuously supplying heat or removing heat, correct? So in the phase diagrams, where are you? Flat line. You're going from one state to another state. I think that's mostly what it was. Am I right? Shall we split? I'll catch you Tuesday. Chapter 5 problem.